Hi guys, I'd like to present an interesting topic to you, which is about the bioplastic derived from the castor oil. Plastic, a so-called wonder material, has become an essential in modern life. The global plastic demand has increased from years to years. According to the American Chemistry Council, the plastic production is anticipated to increase from 308 million tons in 2018 to 756 million tons in 2050. The fossil-based plastic produced is mostly applied for the packaging sector, where they can only be used for once, followed by a rapid transition into the waste state. There are around 7 billion of the 9.2 billion tons of the plastic that generated between the 1950 and 2017 are transformed to the plastic waste. The growing rate of the plastic production has burdened the current waste management system. The fossil-based plastics is usually not biodegradable and will persist for a long time in the environment. Since the plastics are non-degradable, the waste plastic is typically incinerated, which produces dioxins and enhance the carcinogenic emissions. More than 65% of the plastic waste collected have been ended up in landfills or be incinerated. To address the global issues with plastic pollution, waste disposal, and the depletion of the non-renewable resources, the research interest of the polymer scientists has been directed to develop the biopolymers. Plant oil is one of the renewable resources that can be used to produce bioplastic. The plant oils such as soybean oil, olive oil, and castor oil are economical and less prone to the fluctuations of the global oil market. The fatty acids of the plant oils may serve as the starting material to synthesize the biopolymers via different chemical modification methods, and among the plant oil, castor oil has drawn attention due to its availability, cost effectiveness, biodegradability, and eco-friendliness. Now, let's learn more about the castor oil. Castor oil is a non-edible oil that can be extracted easily from the seed of the Ricinus communis plant. 90% of the world's castor oil production is produced in India, which is followed by China and Brazil. The production of the castor seeds is estimated to be 250,000 tons per year, and the oil content of the castor seed is ranged from 45% to 50%. However, the oil yield of the castor seed is low as compared to other non-edible oil seed, which is just around 0.45 tons per hectare per year to 1 tons per hectare per year. The fatty acid composition of the castor oil is shown in this figure, and the castor oil contains 90% of the racinoleic acid, 4% of the linoleic acid, 3% of the oleic acid, 1% of the palmitic acid, and 1% of the stearic acid, as well as a small amount of the linolenic acid. The high content of the racinoleic acid makes castor oil to be distinctive among other plant oil, as these unsaturated fatty acid monomers could provide additional natural chemical functionalities for modifications, cross-linking, and polymerization. This makes castor oil a suitable alternative for polyurethane synthesis. Polyurethane, referred to as PU polymer in short, is an important class of polymers. This polymer is advantageous as it can be tailored by the final user to meet a wide range of specific requirements. Hence, some of the early stage attempts to turn the renewable resources into polymers were made in the field of the PU polymer. PU polymers are formed via the chemical reaction of the polyols and isocyanate, which results in the formation of the urethane linkages. The castor oil can be used to prepare the polyols that require for the PU polymer production. The polysynthesis from the castor oil can be done through two methods, which are the photochemical thioin reaction and the nucleophilic microaddition reaction. In the first method, a thiol group is added to the double bonds of the castor oil under UV light to form the thiol ether bonds with the presence of the 2-hydroxy 2-methyl propyl phenol as the photoimide. initiator. The photoinitiator will be decomposed into two free radicals by the UV light, and the two free radicals will then transfer to the thiol groups to produce other new radicals. The new radicals produced will be added to the double bonds of the castor oil, and such radical chain reaction will continue to happen as the newly formed radical will transfer again to the thiol group to generate the new radical. And the mechanism of the first method is shown in this figure. The second method is the nucleophilic microtoluene reaction. The reaction is catalyzed by bases, and the base catalyst will transform the thiol groups into a strong nucleophile, which is then will be added to the activated double bonds. The double bonds in the hydroxy ethyl acrylate is activated by the electron withdrawing effects. And the mechanism of the second method is shown in this diagram. The mechanical properties of the four different PU polymers that derive from the castor oil polyols are summarized in the table 2. Based on the table, it has been noted that the PU polymers that produced by curing the polyols that produced via method 1 with the HMDI isocyanates has the best mechanical properties. This PU polymer has the tensile strength of 5 megapascal, elongation of less than 10%, modular strength that range between 244 to 500 megapascal, as well as the highest hardness value. It is also observed that the performance of the PU polymer that derive from the HAMI isocyanate is generally better than the one that derive from the SDY isocyanate. This result suggests that the cycloaliphatic isocyanates will increase the rigidity of the PU polymer produced as compared to the aliphatic isocyanates. And basically, there are two suggestions on improving the quality of the PU polymers produced. The first one is to cautiously control the content of the HMI that utilized as the isocyanate in the PU polymer synthesis process. As mentioned, the HMI isocyanates could increase the rigidity of the PU polymers via the formation of the highly cross-linked polymer network inside it, so that the polymer produced will not be too soft or pliable. However, the PU polymer will be inelastic if the HDMI content is too high. Hence, the HDMI content should be controlled appropriately when synthesis the PU polymer. Furthermore, the quality of the PU polymer produced can also be improved through the glycerol addition in the synthesis process. It is found that the application of the glycerol will lead to the formation of the cross-linked hard and soft domains within the PU polymers and also cause a promotion of the hydrogen bonding. As a result, the hard polymeric domains that form will be more than the soft polymeric domain. As the cross-linking density of the PU polymer is increased, the tensile properties, hardness, and the chemical attack resistance of the PU polymers created can be enhanced as well. Additionally, the hard polymeric domain form will also promote the biocompatibility of the castor oil-based PU polymer. In conclusion, the non-edible castor oil is a good renewable resource for making the bioplastic because it does not compete with the edible oil and hence will not cause any food security issues. The researchers also believe that the castor oil-based PU polymers have a huge way for innovation in the biomaterials fields, such as bond tissue engineering, replication of the medical devices, and wound dressing. Also, in the age of the bioactive materials, it is important to include the design criteria with additional properties like antibacterial activity, which can increase the performance of the biopolymers and also increase its value. So that's all from me. Thank you for listening till now.